Hello, this is Al. I'm the Application and Service Manager here at Electron Microscopy Sciences, and I'd like to walk you through the setup and troubleshooting of a sputter head insert for the Q150 series coders that we sell via Quorum Technologies. This is what a new sputter head looks out once you take it out of the box. On the back side you have registration pins which tell the Q series coder what insert you've installed. It does this by a series of steel pins that interface with the lid. I'll show you that a little later. The grounding cord and the power cord for the sputter head. On the back side we have a couple of components to note. We have something that's called the dark space ring, and it is secured to the insert via 4 hex head screws. That are just hand tight. You just rotate and remove the dark space ring. Underneath you have the target retaining cap, which is simply screwed into place. This is the target backing plate, which actually you can dislodge and fall out, have it fall out to reveal the magnets of the magnetron sputter head here. Please don't mess with those. Those are not to be removed. So the first step would be on a new sputtering system is to install the target. This happens to be a chromium target. There's a list of materials that the system could potentially sputter. The 150R series systems are limited to sputtering silver, gold, palladium, and platinum. All the other metals cannot be sputtered. The turbo pump system, the 150T series or V series, can sputter a wider range of metals. This happens to be chromium. So the target is typically 0.1 millimeters thick. They could be up to 3 millimeters thick. One of the problems which I encounter quite frequently is somebody wants to use a thicker target. If you use a target thicker than 0.1 millimeters, you need to install this target dark space ring spacer. That's installed by removing these 4 screws, placing this on the sputter head, putting the screws through it, and this raises up the spacer by a couple of millimeters, preventing the sputter head target retaining ring from shorting out to the dark space ring. When this cap is fully screwed in, it has a set distance, and once it's screwed all the way down, you can just gently move the target so equal distance of target material is seen under the screw, through the screw holes. Now people will ask, well, why don't you have a larger target that just fits in there and is well centered? Well, simply all the target material that's under the rim here is wasted in the end and needs to be reclaimed or recycled. So targets are sold by the size, and with precious metals or rare metals, you don't want to waste that extra amount having it underneath the ring and eventually not being used at all. So the typical target size is 57 millimeters, even though you could probably fit a 63 millimeter target in there, but all that extra would be wasted. So in the end, we don't recommend that you do that. So when the 0.1 millimeter target is installed, the ring does not screw all the way down. And the dark space ring needs to have a space between it and the target retaining ring. And if you use a thicker target, that closes the gap and can create a short, preventing the sputtering process to occur. Actually, you'll get an error message that the sputter insert is shorted out. We'll talk about that more. So once the target is, retaining ring is screwed down on the target centered, you can gently tighten down all 4 screws, and I do opposites first. And that's how you insert the target into the insert, and then the insert fits into the top of the sputtering arm, and the connection is made and you're ready to sputter. Okay, so now I replace the brand new insert out of the box with one that has been used quite a bit here in my laboratory at EMS. One of the common problems that occurs after you use these for a while is you need to maintain them periodically, and I say depending on how much you use it determines how much maintenance it requires, but I would say at least once a week if you use the sputtering system several times a day for a week, and you're using metals which are easy to flake in the vacuum system. So one of the common problems that occurs is you get an error message, there's a short on the sputter head. Well, the vast majority of the time, a piece of metal flakes off the rim of the inside of the dark space here. You can see sort of the metal has bubbled up a little bit on the inside. Yes, this is highly magnetic, and that's a steel hex screw. So what happens is you get a short. A piece of this metal will flake off and go from the dark space ring, which is at ground potential, to the target, which is at some high voltage potential between 300 and 600 volts. So this shorts out the power supply and gives you the error message. So the way you remedy in the first step is to remove the dark space ring. Again, you just loosen the screws and remove the dark space ring. Now you can see these little metal flakes that are sort of coming out from around the rim of the dark space ring. These are the potential causes of shorts with the sputter head. So the way I deal with it is I just take my hex driver or a screwdriver and I run it around the rim. And as you can see, I've dislodged lots of little bits of, in this case, platinum metal that's been sputtered. So you run it around and you get rid of these shards of platinum. And it's good to do it from both sides. And you blow it out with canned gas. And 90% of the times that will correct your problem. Then you would just dust off the actual sputter head just to make sure. And then you'd reassemble and you would find that you no longer have a short condition on the sputter head. Another possibility that occurs when you see a short condition is you've just replaced the target with a new target. The target is much thicker than you used before, and this causes this ring to be raised up closer to the dark space ring, creating a short. If you're using 0.1 millimeter targets and you go to like a 1 or a 2 millimeter thick target, like, you know, go from 0.1 to 1 millimeter, this raises the dark space ring up some increased distance, about 1 millimeter with a 1 millimeter target, and this creates a short condition because the target ring at plus 600 volts is now in contact with the dark space ring, which is at 0 volts, and that creates a short. So if you're using a thicker target, you need to insert the spacer, which is about 1 millimeter plus. You remove these 4 screws, you put the spacer over the holes, you insert the screws back through the holes, and this will give you an additional distance between the dark space ring and the target. That's the second scenario which I see quite frequently. So again, I'm going to tighten this down. Just hand tight, put the dark space ring back in place and tighten things down. Okay, so what if you've done all this and you still have a short condition indicated by the computer in the system? Well, the way I would troubleshoot it, if it happened to me, is my next step would be installing the insert without the dark space ring and test it. If your short condition goes away, well then there's something still contacting between the target or target retaining ring and the dark space ring. Removing this removes the dark space ring from the equation and any possible short condition on the sputter head, with the exception of the sputter head has a fault which would require sending the sputter head to me. So the other possible short is this is a insulator, this material right here. It goes underneath the entire sputter head assembly that's in the vacuum system. Sometimes this can arc because you're using high voltage and it burns through this insulator material and now is shorting directly to the metal of the insert. And you can You may or may not be able to diagnose it via an ohmmeter. If you touch your ohmmeter to here and to here, it should show very high resistance in the megohm range. If you touch the one lead of the ohmmeter from here to the center pin, you should have high resistance. This is not completely diagnostic of a small burnt hole in the insulator material. Sometimes it really requires a visual inspection to identify it, because what might be a high resistant situation is quite different under high voltage conditions. High voltage can jump little gaps in spaces which would show an open or high resistance, and that's why the sputter insert would need to come back to me for advanced diagnostic situations. I would take apart the entire sputter head. I'd inspect for little holes in the insulation, and just routinely, since I've taken it apart, I would replace the O-rings so there was no vacuum leak. I would also replace the insulator just in case I was missing something, clean everything up, put it back together, and test it. So that's some advanced care for your sputter insert. I can now address some additional questions and things that would pop up. As you know, you're not getting a plasma at the light, you're getting a plasma error. We can go through those on another video. Q150 series process optimization. Take one. 3, 2, 1. Hello again. This is Al. I'm Service Manager and Applications Manager at EMS. We're sitting in front of a Q150 VES series coder. We're going to go over optimization of sputter process in these systems, and it's pretty much the same throughout the entire Quorum EMS Q series coders. Doesn't matter if you have a Q300 or a Q150, it's all pretty much the same. The sputter process is sort of a universal thing across the board. We're going to pick a process here, and we'll dissect the parameters on the display so you can get an idea how to optimize your sputter process. And this is according to me, but I do have a lot of experience with sputtering materials, 30 plus years. So if there's some issues, this can minimize the sort of problems that you see, like, you know, plasma ignition problems and such. So this is my typical platinum sputter process for this Q150 V Plus. I usually name it just for the material that I'm sputtering, and then alter the parameters. I don't make individual processes for different amounts of platinum. I wouldn't make a 5, a 10, a 15, 20 nanometer process. I would just make one platinum process and alter the the parameters to suit the experiment. So right now I have it very low sputter current. I won't go into why I might pick these parameters. I'm just saying that these parameters are sort of universal. There are certain ones that I would change on a regular basis. Sputter current, terminate thickness would be two items that I would change frequently on this particular menu. Typical default sputter current for platinum is 30 milliamps. So I'll set this to 30. Terminate thickness is 5. I'll just leave that. That's not so important right here. I'd scroll to the next menu. The default gas bleed time that you get with the system is about 15 seconds. I don't agree with this. You're letting argon gas into the vacuum chamber. And for the sputtering process, you really need a homogeneous atmosphere of argon. So I set that to at least 30 seconds. You have the option to setting it to the maximum of 60 seconds. But I sort of, double the amount that it arrived with from the factory. This allows the gas to go through the chamber, get up to the sputter head, because the gas goes in through the base plate of the system where ignition takes place. This is one of the simple things that you can do to improve the chances of your system lighting a plasma. Other things that disrupt the flow of argon in the chamber is if you're using a large wafer chamber in the Q300 series. This acts as a barrier for the argon atoms to go from the bottom of the chamber to the top. So increasing the gas bleed time certainly improves the gas dynamics inside the chamber. Okay, some of these others I won't play with. I found no need to. The bleed vacuum is another important parameter if you're having plasma ignition problems and faults. For platinum sputters really nicely. You get very nice grain size at low sputter currents at low bleed vacuum. The bleed vacuum essentially is the amount of argon that's let back in the system after it pumps out for the sputtering process. The lower the gas bleed, the finer the grain size, the higher, the larger the grain size, and also it makes it easier to strike a plasma because there's more argon available for that process. So if I were having plasma ignition issues, I would raise the bleed vacuum from its current 5 to the minus 3. I'd go to 8 to the minus 3 to start. And then perhaps even 1 to the minus 2 if I needed to change it further to improve the ignition process. Now, the red circles with the lines through mean that that parameter was changed. As you can see, I've not changed any of the others from factory default. The third page is really not terribly important. Those are the main things that I would change. Sputter current, gas bleed time, and bleed vacuum if I were seeing plasma ignition issues. One other thing that causes plasma ignition problems is the oxide layers on metals like chromium or aluminum are preventing it from occurring. What I do before I install a chromium target or an aluminum target is I get a 240 grit sandpaper, wet to dry sandpaper, put a little bit of water on it or isopropyl alcohol, and I polish up the surface that is going to be sputtered from, and sonicate it afterwards in IPA to remove any grit or debris from the face, dry it off, reinstall it in the sputtering system. You'll find that pre-cleaning the target face via sandpaper will improve the plasma ignition and shorten the amount of sputter cleaning the system will need to do before it actually sputters onto your sample.